Today we're going to look at examples of volume problems. Oh, no, I did. I just forget. I'm just so used to starting over here. Okay, we'll leave that over there and I'll move over. Okay. So let's just quickly recall the formulas that we wrote down yesterday. But I only really want to recall two of them, because from two of them you really can get everything else. Okay. So first, and remember, it's the picture that it's really good to have in mind. So the first picture is the one where we have two functions, f of x and g of x, and we bound a region between a and b, and we rotate around the x-axis. Okay, so you take this region in here, and you can see it pulling out from the board and spinning around, right? That's our drill bit. So here you have, right, a variable x, and your functions are given in terms of that variable x, and you're rotating around the x-axis. Okay, so there's just one letter, right? X-axis, round, f of x around the x-axis, and so forth. Right? So the volume is just going to have 1 pi. And then you remember the pi comes from pi r squared. So you're going to have to square something. Okay, but first we'll put in our limits. And remember, the way this one worked out is you actually were using the disk method on the whole thing minus this piece in the middle. Right? Because if you took the whole thing around, including this bit, you get too much, so you have to subtract out what happens when you rotate that around. So you actually get f of x squared minus g of x squared dx. Okay, so when you have one variable you're talking about, f of x, g of x, right, and around the x-axis, you have just 1 pi, and that's your formula. And in the special case where this g of x is just the x-axis, okay, that was actually the original disk method that we wrote down. Well, in that case, the g of x is just 0, and you really just get this pi something squared. Okay, but if you remember this picture and this formula, of course, you can get that original one back from it. Okay, so you just have to remember this one. And then, of course, we also had, right, where we rotate this, and we have two functions of y, and the area is between the two functions of y, and you rotate around the y-axis. And do you remember what you did in this case is you just swapped all your x's into y's. Right? So if you can remember the x formula, the y formula is the same. Just put y's instead of x's. Okay? Okay, so this is, right, this is coming from the disk method, right? And this is actually what I called the washer, okay, or what I really wanted to call the difference of disks. Okay? But let's just generally call this disks. Okay, this is not how it's normally done in textbooks, by the way. I mean, that's not how they call it. But I don't want to introduce so many words that you think that there's actually a lot going on. There's really only a couple things going on. Okay, the other picture we had was where we actually don't have anything in these three quadrants. Right? We just have something in the first quadrant. The picture is actually the same. Right? Other than the fact that now we're in the first quadrant. But instead of rotating around the x-axis, we're going to rotate around the y-axis. So there's your y-axis. Okay, so there's really only the two things you can do: rotate around the x-axis, rotate around the y-axis. Right. And, well, now you have two letters you're worrying about, right? You have your functions of x x, and the y-axis, right? 2 letters. So how many pi's do you get? 2 pi's. Yeah. Okay, so this formula has 2 pi's. It's going to go from A to B. And, well, in this one, you got to remember that this 2 pi is coming from like 2 pi r. Okay, except in this case, the r, the radius, is the x value. So it gave you an x. And then you had to have, right, the height of the cylinder, which in this case is f of x minus g of x dx. Okay, and this is, well, we actually called the difference of shells. Okay, and the first shell, remember, is when g of x was just 0. Right? And then, of course, this g of x goes away, and you're back to the original shell formula we had. Okay? But you can actually just remember this one formula, and you can recover that other one from it. And, of course, there's the y version of this, where we have in the first quadrant, we have an f of y and a g of y. And we rotate around the x-axis. Okay, so again, you have 2 letters, y and an x, so you better be in the 2 pi situation. And you just turned all your x's into y's. So there's not that many things to remember, I think. There's just a couple, right? You have the original disk situation where you allow it to go into the first or second quadrant, right? But you only have one variable to worry about. You rotate around the x-axis, right? And then you only get the 1 pi because you just have the one variable, x. Okay? And then you have to square things because of pi r squared. Okay? In the shell situation, everything's first quadrant. Right? But you have 2 variables because now you're taking your variable x, but you're rotating around the y-axis, so you have 2 pi's. Right? 2 pi x, right, coming from 2 pi r, and then right, these are the height of the little cylinders. Okay, so those are your 2 formulas. That's what could be easier. Well, if there's only one formula, that would be easier. But this isn't so bad. 2 variables, 2 pi. 1 variable, 1 pi. Okay, by the way, that's just a coincidence that it's 1 and 2. I mean, that's not mathematically, justified. That's just a mnemonic for you. Okay, any questions about this setup? Okay, so let's do some examples, yeah? I think you'll see it's, and we're going to start light. The examples will start, I think you'll find them very straightforward. And then we'll try to push them to be a little bit harder, but we'll just have a nice, easy trick for handling those. So I don't think this should be so bad as everybody who's taken calculus before thinks it is. Okay, so let's start. Here's an easy one. We're going to look for an area bounded by y equals x squared, x equals 1, and x equals 0. And we're going to rotate this around the x-axis. So rotated around the x-axis. Okay, so on all of these problems, the first thing you're going to want to do is graph them. Right? Now, at this point, we're not worrying about graphing the 3D image that you're going to get. And we can worry about that later if we want, but we at least want to graph the area that you're bounding. Right? And why? Well, once you know the area that you're bounding, you can just figure out, oh, which situation am I in? Yeah? Okay, so graphing this shouldn't be so hard. Okay, y equals x squared. All right, well, that's just a nice parabola. All right, so there's our y equals x squared. X equals 1. All right, so we'll put it about there. All right. And x equals 0. Right? Well, that's actually the y-axis. Okay, so we're trying to bound the stuff there. Well, I wonder if I should say, yeah, I probably want it above y equals 0, yeah? Otherwise, it's not going to be very interesting here. So let me add that in there. Right, above, or we want everything above y equals 0. So I'm looking at this region right here. Okay, and I'm supposed to rotate it about the x-axis. So that's here. So I'm going to rotate that region around it. Okay, so which case am I in? All right, why am I in the disk method? Sure, right? It matches this picture. And even matches this picture, except for the arrow, right? Here I'm rotating around the y-axis. Here I'm rotating around the x-axis. Okay, so I can use the disk. I do want to let you know, and we'll see it in an example, there are going to be cases you can use either method. Right? And they'll give you the same answer, but maybe one way is easier than the other. But for now, and in fact, we could do it on this one, in fact. We would just have to change all this variable into a y. And, I mean, x equals the square root of y. But let's just do it nice and directly. We'll use the disk method. So, well, by the disk method, we know what the volume is. Yeah, there's just x and x, so it's pi, 1 pi. Okay, now let's see here. We're integrating from 0 to, let's see, that was a 1, right? Make it more visible, right? So we're going from 0 to 1. And then we have to put in, well, let's see, the top function squared minus the bottom function squared. And what's the bottom function over here? Yeah, it's just y equals 0. Okay, it's that bit right there. Okay, so there is no bottom function, right? We're back into the original disk method where there's just the one function. Right? So we just need to put in here f of x squared. Well, f of x is here x squared. And you have to square it. Right? You have to take your function and you have to square it. That's what the formula says. And now it's just a simple matter of evaluating this. Okay, the pi does nothing. Okay, x squared squared is x to the 4. See, that's nice. If you forget whether you're supposed to add or multiply, in this case, it doesn't matter. But what is it? Are you adding or multiplying? You're multiplying. Very good. Okay, so x to the 4th. You integrate x to the 4th, and you get 1/5 x to the 5th. And then you have to evaluate at 0 and 1. Of course, when you evaluate at 0, you just get 0. Right? So that's no problem. So you just need to put in 1. That's just going to be a 1, so you just get pi over 5. So that's the volume. Whatever of course, in reality, right, when you're computing volume, there's some units involved. But, okay, we don't worry about units here. We just worry about the number. So the volume is pi over 5, whatever the unit is. Not so bad, yeah. Seems like it should be harder. It's not. Okay, let's try another one. Let's just fudge the region around a little bit. So we're going to, again, take y equals x squared. This time, I'm going to only look at x's between 0 and 2. Let's see. What do I want here? Oh, I'm going to bound it by y equals 4. And x equals 0. Okay, so seems to take a lot to describe this region. Okay, and we're going to rotate this time the y-axis. Okay, so again, first thing we do. What's the first thing we do? Graph it, very first thing. Okay, so let's see. We'll draw our y equals x squared. Okay, now we're going to look only between 0 and 2. Okay, so there's 0, 1, 2. And let's see. So we're going to do that. Okay, so this is the line x equals 2. And let's see, we have y equals 4. Now, if we're clever, we think for a second, okay, when you put in 2 into the function, you get 4. So actually, the line passes right through where these two lines intersect. So y equals 4. And then we're bounding by x equals 0 as well, right? So this is x equals 0. Okay, so what is our region this time? Is it this guy down here again? Well, it would be if I didn't put in this y equals 4 business. But the y equals 4 tells me that I'm really trying to bound this stuff. Right? I want the stuff between y equals 4 and this graph. Okay, the stuff down here is actually between y equals 4 and the axis that's somehow also bounded by this graph. So here I just want this. Okay, and now I'm supposed to rotate it, instead of around the x-axis, around the y-axis. Okay, so we need to figure out what situation we're in. So I hear disk around y-axis, and I hear shell. Well, let's take a look. Let's try both ways. Somebody's got to be right. It's one of the two at least is right. So, okay, what should we try first, disk or shell? Shell? Okay. Choose the wrong one. Well, let's try shell. So Genesis shell, we'll try shell. Okay, so in the shell case, if you're going around the y-axis, then your functions should be in terms of x. Okay, now, so here we have a function of x, y equals 4. Not a lot of x's, but it's still a function of x. And here we have a function of x, y equals x squared. Okay, so the volume is supposed to be, well, since there's two things going on, it's the 2 pi formula. You have to integrate from 0 to 2. And now you have to do your top function minus your bottom function, just like with areas. So the top one is 4 minus the bottom one is x squared. And, of course, you can't forget, right? 2 pi should come from 2 pi r. In this case, it becomes 2 pi x. Yeah? So when you do the shell method, right, and you rotate around the y-axis, you use as your limits of integration the x values that you're bounding between. Okay? We'll see it happen the other way when we try the disk method. Okay, so in this case, it's 0 to 2. 2 pi comes from 2 pi r, which means we put an x. Okay, and then we have the difference of our functions. So here you have 4 minus x squared dx. Okay, fine. Let's just leave it like that for a second. We'll go back and see what that is. All right, let's look at from the disk point of view. Now, from the disk point of view, you need to have the variable and the axis match. Right? So we have to turn our heads, right? We know we're rotating around the y-axis. So to make the variables match, we need to write our functions in terms of y. Right? So now, okay, I'm actually bounding between these two functions. Right? Between here and here, between 0 and 4. And I'm bounding between these two functions. So, well, first, if it's the disk method, we know there's just one variable, so 1 pi. You integrate. Now your y's are going from 0 to 4. Right, that's what Chris was getting at. Okay, and now it's supposed to be the square of your function. Okay, and then you have to take the difference. But in this case, okay, we have one function, and then we're going to subtract this bottom function, which is actually 0. Now, okay, so there's not going to be that second function. We just need to have this function squared. Okay. Well, let's look at our original thing. We want to get a function of y. So we need to write x equals a function of y. Right? Well, y equals x squared. How can I get just x? Take the square root. Do I take the positive square root or the negative square root? What did you say? Both. Okay, so both, of course, give you something, right? Which one matches our situation, though? Right? Well, let's see. If you write x equals the square root of y. Okay, so here, when you plug in y values, you get out a positive number because it's the positive square root. So your x's should be positive. All right? And sure enough, on this part of the graph, the x's are positive. Right? We're in the first quadrant. All right? If we put a negative square root here, then the x's should be negative. And that would be if we were over here. Okay? So we want the positive square root. Okay? So that's our function now. Right? Square root of y. And then we have to square it. Right? Because that's what we're supposed to do in the disk situation. Right? You take your function and you square it. It comes from pi r squared. Okay? Pi function squared. And then we integrate with respect to y. Right? Because everything's y. Okay, so those are our two integrals. And those don't look like they're the same thing, do they? Okay, well, maybe we should figure them out. All right. So let's compute this. So in our first one, we go from 0 to 2x times 4 minus x squared dx. Okay, so this, let's see, let me just expand this, right? That's easy. I mean, you can do substitution, but come on. This is 4x minus x cubed. And, okay, integral 4x to x squared and minus x cubed. Okay, and then we have to evaluate at 0 and 2. All right, so let's see. When we plug in 0, these all go away. So we don't have to worry about 0. When we plug in 2, okay, you get 2 squared is 4, times 2 is 8, minus, right, here 2 to the 4 is 16, divided by 4 is 4. So 8 minus 4 is 4, times 2 pi is 8 pi. Okay, let's try the other one. Okay, so the other one we have v equals pi times the integral from 0 to 4. And then we do the square root of y squared dy. And, of course, the square root of y squared, this is quite nice. Yeah, this is not so bad. Okay. So let's see. Integral of y is, of course, just 1/2 y squared. We evaluate at 0 and 4. When you evaluate at 0, of course, it goes away. So we just have to evaluate at 4. So you get 4 squared is 16, divided by 2 is 8, times pi is 8 pi. That's pretty nice, yeah? It's a little surprising that these two different integrals pop out like that. This reminds me. I need to send you guys, maybe I'll put on a homework. It's a very surprising integral. No. Okay, so who was right? Me. That is a perfect answer. Yeah. Okay. So in this case, you could use either method. Yeah. Now, which answer do you think is shorter? Maybe the disk is a little bit shorter. Yeah, it's true. Yeah. Okay. So maybe they're about equal. So in this case, and this is actually really good because I hate for anybody to come away thinking there's one method that is the better one, right? Because they're both good methods and they're useful in their own situations, and sometimes they overlap. And there are cases where one is going to be decidedly better than the other. Right? This is not one of those cases. Right. Any questions? Is it pretty straightforward so far, you think? Yeah, it's not so. Well, you know me. This is your point. Will the exam be tricky? Well, you mean my final exam or the exam of life? We shall see, Zul. We shall see. It'll be a surprise. That's good. It'll be a surprise what's on the final. That's good. Has anybody in here watched The Last Starfighter? Never heard? Yeah, it was a big movie in the 80s. If you're a kid, it was huge in the 80s. But yeah, too bad nobody catches my references. Okay, so why don't we try another problem? I mean, so it seems to me that the most important thing about these problems is identifying what method to try to use, right? And then making sure that you have all the right information, you set up your limits correctly, right? You don't say, oh, I'm in this method, do I go the x-axis limits or the y-axis limits, right? You got to sort that out. Okay, so let's try, oh, this is a good one. I'll write it like this. X equals y minus y squared. Yeah. This should make you worry a little bit. And we'll go between x equals 0. We'll bound it between those two, and we'll rotate around the y-axis. Okay, so now you got to graph this guy. I know it feels really bad because you think, oh no, y minus y squared, what in the world is that? Right? But if I'd written y equals x minus x squared, or even better, y equals minus x squared plus x, then you might think, well, I know what shape that is. What shape is it going to be? Parabola, right? So if you switch x and y's, it still has to be a parabola. It's just facing the wrong way. Yeah, you just go. Okay, so, well, how can you draw a parabola with a limited amount of information? Well, one really slick way to do it is first figure out the roots, if they exist. Right? So, for instance, when will this thing be 0? That's one of them. I hear minus 1, I hear plus 1. It can only be one of them. Well, let's see. If you put a minus 1 in here, it's going to square it, and you'll get a 1. And then you'll have here, if you had a minus 1, you'll have minus 2. So it better be 1 minus 1, right, is 0. So, and mind you, I'm not doing this on the x-axis, right? I'm looking for y, what y value is going to give me a 0. So I have to go from There. Now, let's see here. So it's going to be a parabola, and it has to go through those points somehow. Right. Now, if we use calculus, we could actually figure out where the vertex is. Yeah? You should remember how to do that. That sounds like somebody who remembered the formula. Yeah? Okay, minus b over 2a. Well, in this case, what is that going to be? Minus 1 over minus 2. So it's a half, right? So actually, the vertex is lying right in the middle. Okay, so this parabola either goes here and turns around and comes out, or it goes here, turns around and comes out. Which direction does it face? This way? How do you know that? Ah, it's a negative. Okay, so you got this negative y squared. Well, why does negative point that way and not that way? Okay, so this is a good mathematical reasoning, right? Take your parabola and tilt your head with it, and it should go like that if it's positive, right? The negative one, you tilt your head, and now it goes that way. No, this sounds silly, but this is a perfectly legitimate operation. It's rotation by pi over 2, actually minus pi over 2. Yeah, okay, no problem. Okay, here's a naive way to do it. Plug in really, really big values of y. Right? Really big values of y. What happens? Well, that becomes really, really negative, and this y doesn't matter. Yeah? So the x becomes negative. So as the y goes up to infinity, the x has to go to minus infinity. Right? So it better be going like this. Okay, so that's our graph. And now we're bounding things by x equals 0. So we're getting this nice little bulge here. Yeah? Mm-hmm. Okay, first, you need to identify this as a parabola, because it's a quadratic. Right? If this was x squared, minus x squared plus x, you have to know that's a parabola. Same thing with a y. Okay? So it's a quadratic polynomial, so it's a parabolic shape. The zeros give you 2 points on it. Right? Now it could be, usually the roots don't have to be symmetric about the vertex. Right? Is that true? Or do they have to be symmetric about the vertex? On any parabola. Mm-hmm. It's just a parabola, right? No continuity problems. Let's think about it. Just draw any parabola which has roots, and really 2 roots, right? If it only has 1 root, then it's kind of silly because we know. How can you only have 1 root? All right. If it hits the axis and only has 1 root, it can't go down any further. Because if it went down any further, it would have to come up and hit it again. So it can only have 1 root if it looks like that, okay, or the flip. Okay. So in that case, they are symmetric because there's only one of them. Okay. If there's no roots, then of course it's a moot point. There are no roots, so they don't have to be symmetric. All right. So the only interesting case left is when it hits twice. Okay, so say it hits twice. So that hits once there, it hits once there, and there's the vertex. Okay. If you look at this distance, okay, so you look here, x, and you look here, y. Does x equal y? Seems like there's a good chance. How could you tell? Well, Chris, you know the x-coordinate of that point, right? say this is coming from ax squared plus bx plus c. Right? That's the equation of my parabola. What's the x-coordinate of the vertex? Yeah, so that's what you told me, right? Minus b over 2a. Now, what are the x-coordinates of the roots? How do you find the roots of a quadratic formula? That didn't sound exactly right, but it gave away the answer, yeah? How do you find the roots of a quadratic of a polynomial, right? You use the quadratic formula, so you know it's going to be, right? Well, you don't know which one is which, but you know that the two coordinates are going to be minus b plus or minus, right? That's where the two of them comes from. The square root of b squared minus 4ac over 2a. Right? Now look at this. You could rewrite this as minus b over 2a plus or minus the square root of b squared minus 4ac over 2a. So one of the roots comes by taking the vertex and adding some number, and the other one comes by taking the vertex and subtracting the same number. So, are the roots symmetric about the vertex? Yeah. So actually, right, once you know the roots, you know, right, that the vertex of the parabola is going to be in the middle of them. So once you know the roots, this makes it, and then the direction, of course, by looking at the sign in front of the squared term. Right? If it's minus, it points this way. If it's plus, it points that way. That effectively enables you to graph it. Okay? Isn't it cool what you can do with math? Okay. Very good. So, here we are. So we were rotating, all right, this area bounded by x equals 0 and y minus y squared around the y-axis. So this way. So which method am I going to use? If I'm taking functions of y and rotating them around the y-axis, yeah, I'm in the disk situation. So since there's just the one variable, I must be using the formula where there's 1 pi. So the volume is going to be pi times the integral. Okay, so we need to figure out where we're going. So we said that one root was 0 and one root was 1. Okay, so we must be going from 0 to 1. And now we have to do our top function minus our bottom function. Right? But of course, our bottom function is just 0, so we don't worry about that. Right? And then we remember, oh yeah, we're in the pi r squared case, so we have to square whatever function we put here. So our function is y minus y squared, and then we have to square it. And then we integrate with respect to y. Okay, so this is now just fun time. Fun time, fun time. Okay, so why don't we just expand it, right? Square something, boom. Y squared minus 2y cubed plus y to the 4th dy. Okay. All right, let's see here. Y squared becomes, what is it? Y cubed over 3. Yeah. And 2y cubed becomes y to the 4th, right? And the y to the 4th? And then we're going to evaluate it between 0 and 1. And again, where it's really nice when you evaluate at 0, everything goes away. So we don't have to worry about that. And we just have to evaluate at 1. And all these y cubed, y to the 4th, y to the 5th, at 1, they just are 1. So you just get pi times a third minus a half plus a fifth. And, well, let's see here. let's see, a third minus a half. That's 2 minus 3 is minus 1/6. A fifth minus a sixth is 6 minus 5 is 1/30. So this is pi over 30. Yeah, I leave it to you to do fraction, addition, and subtraction. Okay, so there's your volume when you rotate it. Okay, what do we got? Okay, should we try another one? Let's reset our board here. Okay. Does everybody have this calculation that wants it? Kaiway, you good for it? Okay. Okay, so let's try something only slightly nastier. Okay, we'll look at y equals 1 over x. And bound between y equals 0, x equals 1, and x equals 2. And we'll rotate around the y-axis.
Calculus rules.
Okay, step 1. Graph it. Yep. Okay, so 1 over x looks like so. It's a nice hyperbola. And let's see, y equals 0. That's this nice guy here. And x equals 1. Put that about here. And x equals 2. We can put it there. All right, so our region is the stuff bounded above y equals 0, below 1 over x, in between x equals 1 and x equals 2. And we're going to go around the y-axis. Okay. So, step 2, identify which method. So let's see. We start off by thinking to ourselves, well, let's see. Our stuff is given in terms of x, and we're rotating around the y-axis. So it might be a good idea to look at the shell method. Okay. Now, when you have the shell method, you should have a function on top over a function on the bottom. And, yeah, we seem to have that, right? It's all in the first quadrant. So we can try the shell method. Okay, so we'll go v equals, well, there's x's and y's, so it's two variables, so it's going to be the 2 pi formula. And then we need to integrate between, well, let's see, 1 and 2. Now, because it's the 2 pi formula, you know that's 2 pi r. So you need to put an x in, right? 2 pi x. And then you need to put in your function, the top function minus the bottom function, right? The height of the cylinder. In this case, the bottom function is 0. So we don't worry about the second function. It's just the whole top function. So x times 1 over x. And oh, doesn't that look pretty? It's amazing, right? You would think because it's 1 over x, this region should actually somehow be harder to compute what's going on with it. But actually, the integral is going to be really easy. I mean, isn't that the darndest thing? Can't get much better than that. Of course, in general, just a little aside here, what is the integral from a to b of dx? Not a minus b, but b minus a. Of course, you can do it directly. You can just say, okay, well, this is x evaluated at b and a, and so it's b minus a. Okay. Or you can think, well, what if I graph this thing? Okay, let me start at a and I start at b. My function is actually, I can think of it as 1. Right? So I put a 1 up here. So I'm actually just computing the area of a rectangle with height 1 and base b minus a. Okay? This length here is b minus a. And of course, the area of that rectangle will then be b minus a times 1, which is still b minus a. Okay? Generally speaking, and later on when we talk about double integrals for a little bit, we'll see this. When you have some region, okay, it doesn't have to just be an interval, but let's say you're in 2 dimensions. Right? And you want to find the area of this region. The way you can do it is, well, we'll use a double integral, and if I call this region R, we'll integrate over R. Don't worry about this dA business. And we'll just integrate the function 1, right? Which basically is going to be this exact same situation, right? It'll just give you, in this case, you got the area of a line segment is just its distance, okay, b minus a. Here, you'll get the area of the region. Right? It actually gives you a volume, but that volume is just take the area times 1, and so you know what the area is. Okay, so that's nice, because right here we automatically know, right? The integral from 1 to 2 of dx is just 2 minus 1, which is 1. Yeah? Oh, so remember our function, right, was 1 over x. Right? Yeah, okay. And remember our formula, right, for the shell method, right? 2 pi x coming from 2 pi r, and then you have to take the top function minus the bottom function. In our case, the top function is 1 over x. The bottom function is 0. Okay? You're just bounding it by 0. So you get 1 over x minus 0, or 1 over x. Okay, so this is just 2 minus 1, which is 1. So this whole thing is just 1. So you actually get 2 pi out. Kind of cool. With this you think, and this is kind of weird. Okay, 2 pi, by the way, is the square root of 2 squared times pi. Right? And this would be the area of a circle with radius the square root of 2. So somehow you get the same number out. Of course, this is an area, not a volume. Right? This is a volume. But you get the same number by taking this weird region and rotating it out, as if you just took a circle with radius root 2 and found the area. It's just I mean, there's nothing behind that. It's a coincidence. I just think it's really neat that those things should pop out like that. You know? I mean, you wouldn't imagine that this, when you had, would give you the same volume as, there's area in a circle with radius root 2. I wouldn't have anyway. Okay. Any more questions on that? No? Okay. Perhaps, let's see, are we to the point where, yeah, let's see what time. Okay, so let's do one more sort of easy one, and then we'll start to push ourselves a little bit. Okay, once we're really quite content. No, we haven't started pushing yet. Yeah. Okay. Are you comfortable with these for now? Okay, so. All right, so get all the numbers right. 16 and 0. Okay, so our function is going to be y equals 4x squared, and we're going to bound it between y equals 16 and x equals 0. And I think we're going to rotate around the y-axis. Yeah. Okay. I think I can't see these things. All right, so we got to graph the sucker. So 4x squared, well, nice thing, right? X squared looks like this, 4x squared. Right? You just narrow it up a little bit. But since we can rescale it any way we like, we just draw it like we drew x squared. All right. Now let's see. We're bounding it by y equals 16. So we'll just shove that up there on top. And we're bounding it by x equals 0. So it needs to be bounded by 16, x squared, and 0. So that's pretty clear what it should be, yeah? There's our region. And we're sending it around the y-axis. Okay. So which method should we use? Disk? Okay, so if we want to do the disk method, that means we need, right, since we're rotating around the y-axis, we have to write everything in terms of y's. Okay? So if we have y equals 4x squared, then we have to divide by 4 to get x squared. And then we have to take the square root, and then we have to decide whether we want the positive or negative square root. But things are nice. We're in the first quadrant, right? So we're taking the positive square root. So square root of y over 4 equals x. Okay, that's actually root y over 2, but we know in the end when we use the disk method we have to square things, so we'll get rid of that square root in the end. Okay, so we're turning our head this way, right? We're using this function, which is x equals the square root of y over 4. Okay, and then we're going to be subtracting, well, x equals 0. Okay, that's our other function. So the volume, since, well, let's see. We're doing everything in terms of y. There's one variable, so there's 1 pi. And we're going to integrate from, well, let's see. We've got to go from here to here. So that's 0, and this up here, well, 16. So from 0 to 16. And then we have to do our top function squared minus our bottom function squared. But our bottom function is 0, so there's no bottom function to worry about. And our top function is the square root of y over 4. Right? And we have to square it. And then we integrate with respect to y. What do you think, Hussein? Is that right? Yeah, if you want to use the disk method when you rotate around the y-axis, right, then all your functions should be written in terms of y. Okay. If you didn't want to do that, what method could you have used? Shell method, right? Okay. Let's set that up independently. If we wanted to use the shell method here, well, first, we know there would be two variables, right? The x's and the y's, so there's 2 pi's. Right. And now, we would have been, since we're going around the y-axis, we look at all the x limits and the x functions. So we'd be going from 0 to, we need to figure out what that point is. Right. So what x value is going to give you a 16 for your y value? Yeah, 2 squared is 4 times 4 is 16, so that would be a 2. Okay, so we'd go from 0 to 2. And then we would have our top function minus our bottom function. And here our top function is 16. Oh, no, we almost forgot something, right? 2 pi is 2 pi r, right? So we need the x in there. Okay. Now our top function is 16, and our bottom function is 4x squared. All right, so this is nice because I mean you look at both of these integrals and you know we can solve them, right? There's no question about it. Okay, we're going to be able to do any of these. Okay, so both methods again are going to work. All right. Okay, so we'll just solve it, make sure we're getting the same thing. All right, so one nice thing here is in the first step, when you square the square root, it's just you're just getting a y over 4, right? Because the square root and the square cancel. Okay, and then the 4, you can pop it out. So let's make that a pi over 4, and then you just have y dy. Okay, so pi over 4, and then you have to do 1/2 y squared at 0 and 16. Of course, when you plug in 0, again, everything dies. When you plug in 16, okay, 16 squared is 256. Divided by 2, you get 128. Divided by 4, you get 32. So 32 pi. And if we try to evaluate the other one, let's see, you get 16x minus 4x cubed. All right, so the integral of 16x is 8x squared. And the integral of 4x cubed is x to the 4th. We have to evaluate at 0 and 2. When we put in 0, again, everything goes away. When we plug in 2, so you get 2 squared is 4 times 8 is 32. And 2 to the 4th is 16. So 32 minus 16 is 16 times 2 pi is 32 pi. Okay, so again, both methods give you the same answer. Okay, so are you feeling, at least with these nice, reasonably difficult examples, are you feeling like you could do this? This is not so bad. Okay, so if you've taken this class before, you might remember that there's another wrinkle that gets added in here. And what's that other wrinkle? Exactly, right? You don't have to rotate around the x-axis or the y-axis. We could, right? For instance, here I rotated around the y-axis, but how about what if I wanted to make it a little bigger? And I rotate instead of around the y-axis, but around y equals minus 1. Right? So now it's much bigger. Right? How does that fit into our model, right? Our model doesn't tell us anything about what to do in those situations. At least we don't think it does. All right? How do we win the game? Okay. So we're going to use the following principle, which is actually pretty obvious when you think about it. I'm just going to use nice mathematical words. Volume is invariant under translations. Okay, what does this mean? So volume, all right, well, we accept that we know what volume is talking about. Invariant. Okay, invariant means doesn't vary, doesn't change. So volume doesn't change under translations. What do we mean by translation? Well, I don't mean turning this from English into French or something. Okay? Translation here means moving. Right? If I have a tennis ball and I throw it up into the air, the volume doesn't change. Right? No matter where I look at it, boom, the volume is the same. Okay, that's not quite true. If I throw it up really, really, really high in the air pressure might change and then it might contract and expand. But okay. It's constant, yeah? The volume is constant. No matter where you put the object, the volume doesn't change. Okay, at least in our idealized mathematical world where we don't have to worry about things like air pressure. Okay. Do you buy that? That's pretty clear, right? The area, I mean, the same thing that's true for volume is true for area. Okay? This paper has a certain area. If I stand on this side of the room, the area is the same, right? It doesn't matter. So it may be the case, however, that if you want to compute the area of the paper on this side of the room, that it might be technically very difficult. But if you move it to this side of the room, it might be technically very easy. Right? That's why you would even want to worry about this. Right? It's just in doing computations, it might be easier to compute the area or the volume somewhere else than where you have it. Okay, so let's see an example. Let's take the same picture. Okay, so we had our 4x squared. We have our 16. Okay, so same problem as before, but now let's rotate around. Let's see, I think I want to use y equals minus 1. Where did I put it? Or no, x equals minus 1. So before, we rotated around the y-axis. Okay, around there. This time, I have x equals minus 1. I want to rotate around this. Okay, so this comes out and around it, right? There's going to be a nice big hole in the middle of it. I forgot I was going to bring combos in for everybody. Okay. So the way we're going to solve this problem is by moving our region and calculating the volume in a situation where we know how to do it. Namely, where instead of rotating around x equals minus 1, we just rotate around the y-axis again. Okay, that's how we're going to do this. So how can we do that? Well, if I take this piece and I rotate it around x equals minus 1, that is exactly the same thing, as far as volume is concerned, as if I started with this thing moved over by 1 and rotated around the y-axis. Right? If I just take this picture and shift it over by 1, right? Or if you like, leave the object where it is and pick up the coordinate axes and move everything over. Right? Then it would be the same thing as rotating around the y-axis. So the picture that I change it into, okay, so I'm going to take this picture and I'm going to change it into a new picture. I have x equals minus 1. I'm going to shift that over to the y-axis. To do that, I need to shift everything over by 1. Okay, so that had a vertex at 0. Now it's going to have a vertex at 1. Okay, of course, this line y equals 16 doesn't change a bit. Okay. Before I was bounded by x equals 0, I have to shift that over 2. Now it's bounded by x equals 1. Okay. So it's the same exact region here, just shifted over by 1. Okay, so this is your 0. Okay, and now I'm going to rotate it not around -1, but around the y-axis. And we know how to solve that problem. Okay. Now, there's one little technical thing we got to remember. If I shift this function over, the function changes, right? It was 4x squared over there. It's not 4x squared anymore. Right? What is the new function? Okay, so this was 4x squared. That was y equals 16. This is still y equals 16, but what is the new function? Well, see, how do you take a function and shift it to the right by 1? We don't use delta. This is before calculus you do this. In pre-calculus. Exactly, right? We're going to turn all the, x's into x minus 1s. Right? To shift, do a horizontal shift by 1 to the right, you turn all your x's into x minus 1s. If I'd shifted it to the left, it would have been x plus 1. Okay? So my new function is y equals 4. Now I see an x, so I turn that into x minus 1, and then I have to square it. Okay. All right, so next time, we'll pick up, we'll compute this out, right? But it won't be hard, because now we're back into a situation where we know how to solve it, because we're rotating around the y-axis again. We'll do another one around, we'll take this, and instead of rotating it around the y-axis, or x equals minus 1, we'll do one around, I don't know, y equals minus 2 or something. Okay, just see how that works. And then we'll do some more good examples of it. But I mean, the bonus of doing it this way is you only have to learn these two formulas now, right, and know how to use them. And all the time when you're rotating around another axis, you just shift it back, right? Just shift the whole picture. And because volume is invariant under translations, you haven't lost a thing.